So I'm Vinny Sundaram. This is Michelle Dennison. We're from Booz Allen Hamilton. And we're going to talk today about Model-Based Systems Engineering, or MBSE. So just to give a little context of our background, I'm a mechanical aerospace engineer. Michelle is a mechanical engineer. And we've learned all of our knowledge of systems engineering and model-based systems engineering on the job. So we are learning, we're always learning, and we're here excited for all of you guys to teach you about our knowledge and for you to teach us about what you've learned about model-based systems engineering. So we work out of an office in Los Angeles. We support primarily Air Force contracts. We support the GPS Directorate out in Los Angeles, so we work on a lot of Air Force contracts. We're going to talk a lot of DoD lingo, so if you don't understand anything we're saying, please let us know. I know every professional in this audience will understand that. But we just wanted to gauge the audience. Who here works in systems engineering, has an understanding of systems engineering? Okay, a lot of you.
Great.
All right, so we tried to tailor it to people who both did and didn't, so there might be some information that you might just scan over, but bear with us. All right, so should I go ahead and get started? All right, so we're going to go through a little introduction to what we're presenting today, talk about the concept of the digital thread and digital twin, introduce model-based systems engineering, and how we've worked to integrate different parts of the system lifecycle into our MBSE work, and that includes cybersecurity, program and risk management, software, verification and validation, modernization, and how we've worked towards making the digital thread and our MBSE work exposed to different practitioners and different disciplines within the system. All right, so we're going to start with an example. Anybody from Boeing here? All right. So we decided to go through an example that we'd all understand, a commercial airliner, specifically the 787, because I'm a fan. So 787, or any commercial airliner, quite a big feat as a systems engineer or any engineer to create one of these and to manufacture and sell it to the market. The 787 specifically was a bit of a disruption to the market because it was primarily composed of composite materials. Sorry, wrong direction. So as you can see here, it's 50% composite and less aluminum and steel as they usually are. So what does this mean? This meant that the aircraft was lighter weight. Lighter weight implies more fuel efficient. And this also made them capable of selling a less costly aircraft. So less costly both in initial development, but also throughout the maintenance and the life cycle of the aircraft. Boeing also approached the system design process a little bit different for the 787. They outsourced a lot of their work, a lot of the design and manufacturing. So the reason why they did this was to kind of get a best of breed. So they wanted the best of everything they could get, so they outsourced to the people who do it best. And while this is a good concept in theory, it did require a big integration and systems engineering effort. And if many of you know, there was a lot of scheduling slip and cost slip with the design and manufacturing of the 787s. So another thing they did is they kind of revamped their network architecture, which we'll talk about a little bit later. But in essence, this example is good to understand what good systems engineering is, and we can also learn from the 787's approach, or Boeing's approach, to building this aircraft. All right, so to combat integration issues, we need to do good systems engineering. And why do we do it? So this gives a good example of why we need that person to be an integrator when we're doing an aircraft design. If we have each discipline designed to what they want or to optimize to their needs, we'd get vastly different products. So someone concerned with weight would build a glider, something really lightweight. Someone concerned with flight controls would build something that has all the computation power in the world and no space for passengers. Someone concerned with structures would make it really heavy duty and strong, but it might not be able to even get off the ground. Manufacturing engineer will make sure it's simple and easy to manufacture. An aerodynamics engineer might just make one big wing with no body. And someone concerned with noise would make something very low profile. So we need an integrator in the loop to take all of these into consideration, do some optimization problems to understand if we need to give up a little bit in one area in order to get our final product, something that actually complies with our requirements.
All right. Maybe I'll try this one. So according to that show of hands we saw earlier, I'm sure most of you have seen this before. So the systems V is an overview, a very simplified, high-level concept of what systems engineering is. So you start by deciding what you're trying to do. You're trying to fly a plane in the case of Boeing that transports passengers in a safe and efficient way. And then you need to develop requirements. So thinking of each of those work streams that we just discussed, what requirements are going to make that possible so that everything integrates together? From those requirements, you're able to develop a system architecture. What's your plan? What's your outline? And then you can get more into system design and development. So when you're doing that, you really have to pay careful attention to how all of these different disciplines are going to integrate, how these different pieces are going to come together to work. And then you need to test against your requirements. So you need to make sure that you're meeting your initial requirements and what you set out to do, which is, in this case, transporting those passengers. And then we go into operation and maintenance. So it's evolving to sustaining the system, modernizing where necessary, and improving as you go along. So this house of cards is to illustrate that if there's something wrong in one piece of that system, and it's being integrated with all those other pieces of the system, that error propagates, right? So it's not just isolated to one concern. It goes to everything that's connected because we're talking about a picture that's bigger than just one card. And how do we keep track of everything? Well, I'm sure most of you in industry have seen a lot of paper, and you've seen a lot of different required documentation, especially when things become more important or involve humans and their health and safety. So making your way through all of that paper can often become difficult, and cross-referencing to make changes, design improvements, and modifications is a serious challenge. So we're going to see what can we do about that. And we want to define a digital thread. So a digital thread is essentially a communications framework, and that enables a data flow from all these different sources of information. Here, for example, we have a meeting going on, we have some block definition diagrams, PowerPoint presentations, analysis. This little guy over here is supposed to be sage knowledge. Sometimes there's things about a system that only a person knows. And how do you really capture that information that's in their mind and in their brain? And how do you know what exactly is going on if all of this different information is stovepiped and isolated? By creating the digital thread, we can literally sew together all of these different types of information and documentation so that we can more fully understand our system.
Right. So now we go into the concept of a digital twin. So a digital twin is essentially a digital instantiation of a physical asset. And as a lot of us, I'm guessing, are engineers, we're very familiar with this concept. A CAD model is a digital twin. It's a physical representation of whatever system you're building towards. But a CAD model gives you dimensions, it'll give you some system specs, but there's a lot more we can add to that digital model. So once you port onto that FEA analysis to understand the loads on the system, CFD to understand the aerodynamic loads on the system, we start to get more of a better picture or a better representation of that system true to form. But the digital twin takes that to the next level, and it introduces the idea of retaining that digital instantiation of that physical asset into post-production after it's already a physical asset. So that means including any maintenance data, the operational history of that asset, and this allows us to essentially do analysis on that object after it's already been fielded. So going more into depth about that concept, if we take into consideration wind tunnel modeling, before we had very sophisticated computational modeling and simulation techniques. A lot of the times, in order to test a design and test out the aerodynamics loads on a specific aircraft or rocket or whatnot, we'd have to do a lot of wind tunnel testing. And wind tunnel testing is actually really great, but it's expensive. So oftentimes they'd have several different designs that they put through wind tunnel testing. But what we can do, since we have all of this computational power and sophisticated computational fluid dynamic softwares, we can do a lot of tests up front before we get to the wind tunnel phase. So rather than bringing 10 very, very different designs to the wind tunnel, we might pare that down to maybe one or two, maybe even just one. So that's the power of the digital twin. And I think a lot of us can understand that concept. So the digital twin essentially enables all this data analysis. At post-production, it allows you to monitor your system better. And it creates all these modeling and simulation analyses. And essentially, this helps you reduce downtime, helps you reduce overall cost for production, and any risks that's involved with your system.
So it's pretty clear that the digital twin and the digital thread are great things, but how do we create them? And the way you create a digital thread is through model-based systems engineering, which is a formalized application that supports system requirements, design, analysis, verification, and validation activities, beginning in that first phase of the system V, conceptual design. So we still are doing systems engineering pretty much in the traditional fashion as far as concept development through requirements engineering all the way into transition to operations. But we're connecting all of the data throughout each of these phases by model-based systems engineering. And that's essentially a database that backs all of this up that we're able to access to pull certain information or specific reports. And then we can visually capture the different requirements and how all they are related to the actual physical pieces of the system, their behavior, interfaces, and etc., to trace throughout the system how everything works. So we're doing this because MBSE is a huge advantage, right? We have the centralization of system data, which improves communication. We're all working from the same information. We understand the system the same way because it's defined once and we all access the same definition. We're able to have that single source of information, which I'm sure you've heard, the single source of truth throughout the entire system life cycle, so we can understand what we're working with, where it came from, and why we have those different features and data points. Flexibility and consistency, we're able to create custom reports and custom views so that we can fully understand specific parts of the system. You don't always need to know everything at one time, right? You may want to specifically focus on one area of the system. And with model-based systems engineering, you're able to do that through queries and specific views. So it also helps integrating disparate systems model and analysis with different teams and different geographical locations, different objectives in mind. We're able to kind of understand where everyone's coming from and how it interacts with everyone else's work. So this also enables sharing of data, right? Because the data is in a relational database. Everything is connected. And then we're going to be able to also produce graphical or documented artifacts as required. We're going to talk a little bit later about automatic document generation, and then also about some of the views and how much easier they are to consume as a human being. So essentially, MBSE enables the definition of the digital thread and the digital twin, and it allows systems engineers to focus on value-added tasks instead of as much documentation and data entry.
So while MBSE or model-based systems engineering is implemented using a tool, there's a smart way to implement it, and there's ways that aren't very smart when implementing. But essentially what we get here is, instead of dealing in a 2D design, and what we mean by 2D is a representation of that system that's just purely performance-based, technical, we're able to add a bunch of layers of data that are relevant to systems engineers and different practitioners within the system. So we can add information about cost, cybersecurity, risk, and things like that. So using our ability to query a database, instead of just knowing things, performance or specifications about a fuselage or an engine, we're able to understand any risks related to those specific parts or cost and things like that. So it adds a layer of data to your existing specification models. All right, so what does this mean for an MBSE enabled team? So if we look here, there's different perspectives into a model. So a systems engineer is going to be closely linked with your MBSE, your digital system model, as it's called. They're going to use this information to understand requirements decomposition, or if there's a modernization effort underway, they're able to look into that database and get the proper information they need to perform whatever they need to perform. But this extends past that. We can give views or give information that's relevant for a program manager. So information like risk involved with certain products, cost-benefit analyses, and things like that. And similarly, for a software developer, we can perform software configuration management, things like that. And lastly, for a cybersecurity engineer, we can create network topological views and give them insight into their cyber posture. So essentially what this means is we're using the same database to obtain all this information, but they're tailored to the specific discipline within your system. All right, so now what? So unfortunately, a lot of the times when people are doing architecture or MBSE, it kind of stops at requirements modeling and creating 2D architecture models. But we want to extend past that. So first, we're going to explore how this is done for cybersecurity. So as we all know, most modern day systems have cyber critical infrastructure. So it's very critical to pay attention to cybersecurity. But when designing a system, it's difficult to understand how you integrate that information into your requirements modeling, your requirements development. And also, we can leverage the traceability and the graphical interface of MBSE to understand how our network is set up. So if we look at a basic structure for a cyber asset. So if we know that in our system we want to provide some sort of communication security, provide ComSec. So you understand that functionally, and we might understand or we might know what requirements that speak to within our system. So what we can do here is we can trace those requirements to ComSec related standards. So we can understand when we choose a physical asset what we're actually going to be using to implement our ComSec, they comply with the appropriate standard sets. What we can also do is we can trace IA controls. If you work in the DoD space, risk management framework controls to that asset and track that through its life cycle. So every time you do another accreditation of the system, you'll have the appropriate RMF controls mapped to that system, so you'll know what's relevant for that system. And you'll also be able to track any risks or mitigations that, cyber-related risk or mitigations that you implemented on that system. Something that we have done a lot for a couple programs is helping out with cyber accreditation packages. And that's by providing network topology diagrams or physical network diagrams that capture the network architecture of the system. So essentially, a normal architecture model of your system may not decompose to the level that a cybersecurity engineer needs it to. So we create specific views for ISIs or ISMs, I don't know if I should use that term, but just a cybersecurity engineer, so they can get insight into the system. So we'll make sure that instead of stopping at the component level, we get down to routers, switches, encryption devices, firewalls, so they're able to understand how their devices are placed in the system. So if you look at, first and foremost, we can do a physical data model. So we can, a physical network diagram. So we can understand how all of the IA components are physically connected. And after that, we can do a logical network diagram, and that allows us to understand the data flow within the system. And that's really critical for a cybersecurity engineer to understand any entry points into the network, understand where you're crossing an IA enclave boundary, understand if data is touching a classified component when it shouldn't be. So these are the type of things that we can build out for a cybersecurity engineer. Another thing we can do is add data to everything. So if we have a computer in our system, and that computer is running an operating system and a couple applications, we can tag information like the version of the operating system that it's running, the version of the applications, the level of patch that it's at, any antivirus, any malware software that's on that system, in order to get a good picture of that cybersecurity posture. And all this data in the past has just been queried out of the database. And when cybersecurity engineers are going to accredit a system and get their authority to operate, they're able to get all that information, get these views, and it helps them fill out much of their accreditation packages. So this is just an overview of a system physical view. So again, like I mentioned before, we're able to show any external systems and where they touch the internal system. Make sure they're not touching something with a classified port, here in red. We display the IA enclave boundaries. The blues are the same enclave boundary. The purple is the same enclave boundary. And in addition to that, we can also show location. So if all of this is in one location, all of that's in a different location, it's really important to know that, because physical security is important to a cybersecurity engineer. So this is all we've done using a 2D model, and there's a lot of data behind that as well that helps contribute to a cybersecurity engineer's understanding of the system.
All right, so program management. So having this complicated and intense system well documented and accessible by the program manager is a huge advantage. And that's because mostly of cost and schedule decisions, right? So the program management wants to make sure that they're allocating their resources appropriately, because in every program, resources are limited. And this is a basic show of a cost-benefit analysis, right? It's a rack and stack of different projects that are being investigated by a program, and they're being evaluated according to their reliability data, deficiency reports, cybersecurity vulnerabilities, and all of this is linked to each configuration item within the system. And this is extremely helpful because it allows all of those different data points to be compared against a baseline. So everything's being compared in the same way according to the program's priorities. All right, this goes hand in hand with risk analysis. So risk management is a huge component of every program. And risk management is important because it deals with things that may or may not happen. So for those of you not familiar with risks, I'm sure most of you have heard plenty about them. They're an instance that is weighted on their likelihood and consequence. So if the likelihood of something is 50-50, it may or may not happen. You might not want to address it, but you want to look at how important it is to your overall system. Is it completely destructive? Are human lives involved? Or is it simple as something falling like a painting off the wall, right? There's all different levels and all different scales of this. So in most risk management processes, you go through a cycle, and in the DoD, the Air Force space, we have 5 different phases. Risk identification, which can often be done by a person, right? Something or a subject matter expert realizes that something isn't quite right with the system, something starts to fail, it's a little bit fishy one way or the other, or there could be a data indication. Then you have to analyze that risk. What's the likelihood of it happening? Is it going to happen? Is it a shot in the dark, or is it just an anomaly? You have to really dive deep and understand what the likelihood and then what the impact of that risk occurring is. Once you understand that, you're able to identify whether you need to mitigate that risk right away, wait a few moments, years, all depending on what the situation is and what your score was from your analysis phase. And then once you pick a course of action to mitigate the risk, or if you choose to accept the risk, you need to move on to monitoring it. You can't just forget about it, right? You need to make sure that that mitigation plan that you chose is actually burning down the risk, or if you decided to accept it, that that risk isn't evolving into something greater than you originally thought. All this information is fed back into process planning. So that's the standard risk management process. That's executed all across the Air Force. Those are the guidelines. So what we did is, for one of our programs, we found a way to link all of that information into our data model. So in risk identification, now we had all of this data aggregated, so we were able to more easily identify weaknesses in our system. When we were able to do that, we were also able to use the same data to use a standardized risk scoring. Oftentimes in risk management, some of the scoring can be a little subjective, and that can be dangerous, right? Because something that's important to one person may not really be as important to the entire system. So this gave us a way to standardize across the program. And then in risk mitigation, we were able to see what that, also for risk analysis, we were able to understand a risk that may originally have been thought to only impact certain aspects of a program could actually be far greater than it was originally considered. And then in risk mitigation, we're able to ensure that our mitigation plans or our courses of action are addressing the root causes of that problem. And in risk monitoring, we can measure the effectiveness of that risk mitigation plan. So this is all fed back, and we actually changed the risk process in one of our major Air Force programs. And this is how we did it, right? So we have 5 risk types, different types of risks that were the common types identified by our program, 2 different kinds of mitigations. Each of those mitigation plans is made out of mitigation steps, and oftentimes those mitigation steps were projects, right? So going back to the program management slide, different projects or courses of actions that we can take to mitigate those risks. And then we had the threatens connector, right? What is this risk threatening? Which part of the system is it threatening? What is that mitigation plan reducing? Which part of that risk is that mitigation attacking? What's causing that risk, right? There's always a root cause. And then what is part of that risk and what is part of that mitigation plan? So these are all things that we custom made for our client, and they were very happy to have it. So from this, we have 3 risk views, right? Depending on who wants to know about the risk and what the risk is being used for. Are we briefing to the program manager? Are we briefing to a project team? Are we talking amongst subject matter experts? What are we doing, right? So we're able to take what information we need and display it. So in the blue box, you can see what is more of traditional information that's included in model-based systems engineering. And then in the green and yellow boxes are what we created in our risk architecture profile. So not only can we track cost schedule like we normally would in model-based systems engineering, our digital system model, but now we can also track all of these other data points through tagging them to the element. And this improves impact assessment and guides investment for project management.
So just as every other engineering discipline, we can apply systems engineering principles to software development. So software engineering is very critical because essentially software can pose as a security risk to your system. So you have to make sure that your software is well maintained, is debugged appropriately, and is configuration managed. So is essentially we have to make sure that any changes to our code is well tracked. And we can leverage the tools in systems engineering to do that. And that's another capability that we can integrate with our model. So most model-based systems engineering tools are UML-based, which is the Unified Modeling Language. And we've leveraged our UML tool to perform some of these software engineering configuration management techniques. So what we can essentially do is for any object-oriented language, we can import source code and view it in a visual graphical sense. And vice versa, we can build out code. We can build out these models, these service models, and export it to source code as well. So that's for C, C++, Java, Python, Visual Basic. And another thing we can do with this is we can generate behavioral models, which is one of the type of models that we develop as model-based systems engineers. And I'll give an example. For something like a sequence diagram, which some of you might be familiar with. If there's a certain operation, so if we are deploying landing gear on a plane, there's a set of protocols, there's a set of operations, parameters that need to occur in order for that to actually happen. And some of it is manual, some of it is software-based. So we can track that sequence of things that need to occur in that operation for that operation to occur. And then we can generate code from that. So essentially, we can utilize this tool to do some configuration management processes as it relates to software engineering. And another thing we've done is we've used the tool to do database modeling and database analysis. So this just shows a couple tables not so clean tables, if there's any database engineers in here, for a SQL server, based in SQL Server. So what we can see is we can understand what all of the columns are in a table. We can understand indices into different database tables, foreign keys, the different type of keys within that table, and understand how they relate to different tables. So I'll give an example of a program where we use this in. We were given the problem of a specific program that had several different applications that they were using. And the applications were developed at different times. But each application had their own database, but all of the data in all those databases were the same. They were just formatted differently because different database engineers developed them. And so they were like, they couldn't talk to each other. Application to application could not talk to each other. So they came to us to ask us if we could come up with a way to translate between the different databases and design one core database for all of the different applications. So this is the type of tool that we used to perform that task. All right, so getting to the right side of the V, we get into verification and validation. I don't know if there's any test engineers here, but verification and validation can be pretty arduous. For a system like the 787, there's a lot of moving parts. There's a lot to track, especially if different organizations, different companies are doing your test for you. So there's a way that we can leverage the traceability and all the data that we've integrated into our model for verification and validation. So what we have here, sorry, it's a little bit light, is we have our requirements decomp. And once we get to the point where we want to start testing, performing operational tests and testing against our requirements, in the DoD we have requirements verification plans, which is basically a plan in place to how we're going to test against that requirement. And the requirement verification plans basically decompose into hundreds of test cases. And those test cases can be used to buy down multiple requirements sometimes. So I'll give an example of a screw on an aircraft. So the same screw could be from the same company, and it can be used to attach the wing to the bracket on the fuselage, and it can also be used, internally to the fuselage somewhere. So it's the same screw, and if we have to do the same torsional test on that screw with the same specifications, if we're able to track all this information, we can do it once and not repeat it for every instance in which that screw appears. So it's stuff like that. So if we're able to get an understanding of how our requirements verification plans decompose and how they trace, we'll be able to get a better grounding on, or we'll be able to alleviate a lot of the issues with verification and validation. And moving forward from that, if we're in a more sustainment part of our life cycle and something goes wrong and we want to look back at our historical data for all the tests that we did, it's all contained in the model. So we can look at a specific test we performed, and we can look at the objective that we sought out with that test, when the test event occurred, who did the test, if there were any deficiencies found with the test that we did, and we have all that historical data available to us within the model.
All right, so at the last phase to close out the System V, the digital model is also very important for system modernization. So this allows us to know where we are, where we've been, and now where we're going, right? Where we want to make improvements and how those improvements or modifications are going to affect the entire system. For an example, we just have a basic, really oversimplified model of an aircraft here, and there's an issue that the current engine model needs to be replaced, right? So you have to look at what requirements is that going to affect, and in turn, what element is that going to affect? What's going to change within the system, and what else is that connected to? So this allows you to more easily understand without digging through tons of documentation or interface control documents and tons of other changes that may or may not have been made, what's going to happen. It also allows you to dive a little bit deeper, right? When changes are being made, they're often contested or in a contested environment, And this allows you to show all the information that you need to know. So we can deep dive in and have a centralized discussion with all the key players and all the important parts, and let the system model tell you what's going to happen if you change a specific piece of it. Here we're focusing on this mobile transmitter, so we want to see what's going to happen if we got a new one or change the specs on it.
And also the traceability within the model allows us to understand a project or upgrade, how that affects everything else in the system.
Right.
All right. So we've gone through the arduous process of putting all this information into our database, into our digital system model. So what are we getting out of that? So as we mentioned before, if done well, if done correctly, and if done properly, we'll be able to accomplish a single source of truth and data that all system practitioners can source and can use. And as we mentioned before, we also will be able to generate documentation that's specific to a specific usage. And arguably, most importantly, we can learn about the system. So we worked on an Air Force project for a system that was 50 plus years old. And they'd never fully analyzed their technical baseline. So there were, Visio diagrams here and there, block diagrams. I'm sure you guys have seen this, just random disparate diagrams all over the place, a document that explains a specific subsystem. There was all this information everywhere. So it took a long time. It took 1.5 years, I believe, to put together the full technical baseline. And there were people the sage knowledge people for that system, who understood that system like the back of their hand, who found out things. So it's a discovery process, understanding what your technical baseline actually is. So it's really important to do this just to get a grounding of what your system is. And so this is more for a sustainment system. If you are a system in development, or you're starting to develop a system, if you start this from the ground up, you get a lot of advantages. You get that you don't have to do it after the fact once you lose track of your technical baseline. So what can we get here? So for all different users of the information, we're able to understand how system components interface. We're able to identify all our cyber critical infrastructure and identify any threats or any vulnerabilities in our cyber infrastructure. We're able to understand risks. And to core systems engineering, we're able to understand our activities, our functions, our requirements decomp, and all of this is integrated into our model. So going into document generation, even though we are trying to move to more model-based techniques, at the end of the day, we still are a very document-based system. We function very document-based. So what we can do to get around this is we can generate documentation from the model. So specifically in the DoD, there's a lot of mandated documentation for specific programs. So we still have to create these documents, but if we create it based on the model, then the model still is a single source of truth, and the document can be auto-generated at any time. So we can take our database, it's essentially just a relational database, and we can define these templates to pull specific information from our system database to fill in a document. So for an interface control document, we can define a specific template to define what an interface control document includes, and then use it for any system. So this gives you a lot of power, because instead of relying on the document as a single source of truth, the model data can be updated at any time, and we can auto-generate a document at any time.
All right, so I think we get the idea that this is a really powerful tool, but how do we access it, right? Because not everyone's going to want to learn how to do this, to dive into the model, to have a software license. So one way that we have overcome this is by developing a web app. So a web app provides users with little to no MBSE experience or database experience, an intuitive interface to navigate the model. So basically, we can provide them with an HTML, and they can go and explore, search what they're interested in, what applies to them, and see what their system's all about. So being able to visualize and consume this information is as important as having it there, right? So these web apps can create custom dashboards and help program managers and technical experts manage their programs better. And these are some views from that app that I spoke of. We have a system overview, architecture products, requirements products, interface data, cyber assessments, and project data, things that we talk about all the time as systems engineers that can be queried from the model and used in presentations. This means less time in PowerPoint and more time doing value-added work, which is something I know we all would like. So the other thing that's great about this web app is that it provides access control. So we were able to host FOUO data on this web app and have only people that needed to see it. So they needed to have their CAC or their ID card to be able to access all of this information.
So to give an example, on one program we worked on, we just gave them the URL. They logged in with their CAC, and then they had access to all of the model data. So it was very powerful, and from a client perspective, they really appreciated that.
And what's so nice as the client is as soon as we change something inside the system, it automatically is updated into this app.
But the app itself is read-only, so
right?
They can't change
it, which is also good.
So did you create the app, or is that part of the software package?
Our company developed it, yeah. Who's Alan? Okay, so we're really excited about MBSE, digital twins, and digital threads. We have a lot of fun with it, and all of these examples are things that we've done. So we're really happy to share that with you today. But it's just the beginning, right? This is a long journey into really embracing this digital environment, or the digisphere. So I think that it's going to take a lot of technical evolution, but also a cultural shift, and we hope you all will join us in that. Thank you.
Thank you. All right, if anybody has any questions, there's a mic there.
Yes.
I can probably hear you.
So I apologize if I just missed this, but it's not clear to me if this focuses on a platonic model of the system, or if it has feedback to like deployed instances of components. Like, can I see like the entire history of like the 787 program or components in that? And, I'm not sure how.
Are you saying if when it interfaces with different modeling?
Or different
tools?
versions, like configuration management, what was version 1, 2, 3, 4, 5?
I feel like I heard mentioned earlier in the talk that the like performance of various components was something that could be a part of the model, and that seems like something that aside from testing would also be have feedback from stuff deployed in the field. And so I guess you could see that question differently. I'm curious how deployed in the field artifacts and impact of this modeling system.
Right. Okay, so I will say that we haven't had too much experience with that side of the house I think that's across the board with digital engineering. We're getting into that phase where we try to retain that digital twin once we're post-manufacturing. So we don't have too much experience in that, but I would assume it's a feedback. There is a feedback loop, but it would be static, right? It'd be a capture in time as of right now. So that's the area that we need to evolve into, the technology that we need to evolve into. So that I know there are tools out there that integrate like a CAD model, and you can input operational data and things like that. But again, I'm from what I understand, it is a capture in time.
But we do backups, right? So we're constantly making copies of what that system looks like at that point in time.
There's version control, yeah, but I think for fielded systems, it's a little bit different. Yeah,
it's not automatic.
Yeah.
So I know for one of our larger systems, we have an OMNS contractor who reports all of these different data, right? All these different data points, and then we actually put it into the system to update it. But it's not a direct communication between the tool and the piece component.
Any other questions? Yes. We could probably hear you.
So you said you developed this MBSE model, and this is all in-house. Do you have any examples of software we can buy to get this implemented in our company the right way, so we don't have to develop it on our own?
So that's the thing. the tool the tool we use is the UML-based tool. It's
It's a COTS
Enterprise
tool.
Architect. It's a COTS tool, but you need to know how to use it, right? We used several different tools. A lot of this was in Enterprise Architect. We also use Magic Draw. But again, a lot of this was, learning via implementation. So getting to this stage requires a good amount of best practices, understanding how specifically for that system they wanted to implement some of these things. So the tool itself gives you the means to do it, but it doesn't necessarily give you the processes. So since we are a consulting firm, that's kind of what we do. Our service, our platform is our people. So we go to contractors and government and we set this all up for them. We give them their technical baseline. We give them an understanding of their technical baseline. So it's usually how it works for us. Yes.
So you're a consulting firm and you work with companies when you do this. Have you had any kind of resistance to using the digital twin model? Have any companies been hesitant to trust your data and your process?
Yeah, definitely. I think a lot of the times once we sell it to them, they're more inclined to use it. But the biggest issues we have is sharing data. So that's why we came up with this web app, because you can have all this great data, but if no one's able to see it, then they don't find a use in it. And they're like, why am I paying you to do this? Because I don't know what you guys are doing. And, we want as little effort as possible, because this is not their realm of expertise, right? And another issue that we have in that realm is data aggregation. When we're working on projects that are both unclassified and classified, and we show them this giant thread of data, and they get nervous right away. They're like, oh, wait, everything's connected, So there are definitely situations where people are apprehensive about it, but a lot of the times we display what we've done in the past, and when they see this kind of thing, they're like, okay, I want that for my system. I'm going to find a way to get that for my system. But yeah, it's definitely a lot of roadblocks. Yeah. Yes.
Have you ever used MBSE between companies, some suppliers?
Yes. Make a comparison.
Or even instead of having ICBs to do models instead?
So we coined this term. I don't know if it's been coined before, but we've created interface control models. So instead of using a document to understand something, it's a model that it basically acts as an interface between one system and another system. So we've done something like that. That was between a contractor, an OEM, and the government.
Good segue into my question. You mentioned earlier it's a journey. It's starting.
Yes.
And with that said, one of your slides indicated that you're generating document templates and generating documents. At what point do you forecast you'll stop doing that? We'll just generate models and trade models and stop with stacks of paper.
We try to go with that. That's our first proposal.
We want
at
it
all
now.
times. Yeah.
No,
But sometimes people still want a document.
And
but
sometimes it's required.
Right. Sometimes it's required. It's still mandated. So the idea there is it might be a document, but it's not where the data actually lives. But I don't know when we'll be able to completely cut that cord. Yeah.
Are there any more questions?
We ended a bit early.
All right.
But feel free to come up to us and ask us any questions.
Yeah, thank you guys so much.